say systems of inequalities, there's two kind of sets of math terms there, systems and inequalities. What kinds of things come to mind when we talk about systems or inequalities? Less than or equal to, greater than or equal to. What did you guys say? Okay, but more math related. What does system mean? Yeah, more than one. So it's not just one inequality that we're going to work with. We're going to work with multiple inequalities at the same time. Just like we weren't just working with one equation in the warm-up, we have two equations. Okay. How do you work with inequalities? What do you do with them? Those less thans and greater thans. You could put it on a number line graph, right? So sometimes they're on a number line graph if they're just like x is greater than or something like that. But they could certainly be on the coordinate plane with x and y. What kinds of things happen on the graph for inequalities? Okay, so sometimes there's areas of the graph, whether it's the number line or the coordinate plane, that don't have any points. So then maybe you're talking about open circles, closed circles. What else happens on the graphs? Really big important thing.
It's not like there's one answer.
Yes, there's a lot of answers to an inequality, a lot of things work. I would say almost every inequality probably has infinitely many solutions, unless it's a big discrete set of solutions. But there's probably always some other point or always some other number in between the other numbers. And then what is this that he's trying to do? Shading, right? Shading is going to be really important. So we're going to see those things in our work today. Okay. Now ours are not going to be number line graphs. Ours are going to be on the coordinate planes. They're going to be like line graphs, parabolas, circles, whatever. Okay. So here are some things to note about graphing inequalities. Obviously, you're going to have that whole question of open, closed, but in terms of a two-variable graph, it's going to be, is it a solid curve or a dashed curve? And I call it a curve today because it does, in Algebra 1, maybe Algebra 2, everything you did was linear. It doesn't have to be linear. Solid is going to come from anything with the or equals to sign. So less than or equal to, greater than or equal to, I'm going to draw a solid curve. If it's just less than or greater than, then I'm going to have the dashed curve. There's also that shading where we get the many solutions. There's more than just one single answer. And so my recommendation to you for shading is to go ahead and use a test point. We'll do an example so that you can see me use a test point, but basically you're going to test any XY ordered pair not on the curve. You don't want to pick a point that's actually on the graph because then you can't tell if it's greater than or less than, if that inequality is true, because it will be equal to. Okay, so you want to pick something that's not on the curve. And you basically test it in the inequality. There are two outcomes. It could be true. It could be false. And true just means shade XY. False means don't shade XY. So if it makes the inequality statement true, then yeah, that was the solution. It works. That part should be shaded. If it makes the inequality false, then that point is not a solution. It should not be in the shaded region of the graph, so you should shade in the other portion. You do have some shortcuts, just as an FYI, probably from Algebra 1. If it's linear, and I use these shortcuts too. If it's like y is less than mx plus b, I just shade below the line. If it's y is greater than mx plus b, I can just shade above the line. So less than or equal to is shade below the line. greater than or equal to is shade above the line. There are some shortcut rules for like parabolas, the quadratics, but because you have so many options for quadratics, it could be a parabola that opens up, and then you have outside, inside. It could be a parabola that opens down, and there's an outside and an inside. To me, rather than remembering a rule for all 4 scenarios, it's just as easy to test a point. Okay? So I don't have shortcuts for those. I just only use shortcuts for lines. Okay? Before we get into our first example, I just want to talk about different types of solutions that you're going to see, and this is going to come to us tomorrow when we're looking at linear programming, the different types of solutions. So I'm actually going to have you look, and these are images from your textbook. Look at the middle graph. Okay. In the middle graph, we have 2 lines. This is the line x plus y equals -1, and this pink area is all the stuff that's x plus y less than -1. Then I have another line, x plus y equals 3, and the yellow shading is everything that's x plus y greater than 3. So notice that each individual inequality has a set of solutions, but when graphed on the same line, they have no overlap. So if we're talking about those two as a system of inequalities, this middle graph would be the case of no solution. Even though there are infinitely many solutions over here in the pink, there are infinitely many solutions in the yellow, there is no overlap where one point works for both inequalities. So it could be no solution. Okay. No overlap is a possibility. Yes. Of all the shaded pieces. Yeah. So over here, do you see how there's like basically, what is there? 1, 2, 3, 4 different lines. Okay. And some of the lines like are shaded below the line, and then other lines are shaded above the line. Okay. And then where everything overlaps is this little quadrilateral right here. Okay. This is called a bounded solution, meaning it has some curved boundary on all sides. It's closed. If you think geometry is like a polygon. Okay? It's got some points and their sides all the way around it. Bounded solutions, you'll be able to find places where the curves intersect. In this case, they're all lines. But these points where they intersect, they're called vertices of the bounded region, and that's something we're going to talk about tomorrow when we do our linear programming. We're going to need to know what those points are on the bounded region. Okay. Now there are some points like where like the full overlap does not match that intersection. So there's a point up here where 2 lines in the inequality system intersect, but it's not next to the overlap section. So this is not considered a vertex of the bounded region. So you might have some curves that are intersecting, but if it's not where the full overlap is, then you don't have to find those points as vertices. So that's bounded, and then over here on the right side we have something called an unbounded solution. And I'm sure you can kind of look at this and see I have 2 boundaries and 1 vertex point right there for my solution set. But we can imagine, and our brains can fill in, it's just going to continue to grow as we move towards x approaches negative infinity. So there's no bound over here. Now again, that'll come into play tomorrow when we do linear programming. We'll have some different answers when we have unbounded regions versus bounded regions. Let's do an example. We'll do 1 graphing and 1 setup. So we want to graph a system of inequalities and then also find the vertices for negative x plus y squared greater than 0 and y greater than or equal to x minus 2. Now I could really pick any kind of curve that we've studied previously or that you should have studied previously in Algebra 2 and ask you to graph that curve. Something interesting to note, if I'm looking at this very first curve right here, negative x plus y squared greater than 0, we don't normally see a lot of equations that look like y squared, right? Usually if we see a squared, it's x squared. So what shape is x squared? The parabola, but you've always seen the parabola open up or open down. So when we switch it and we make it a y squared, now our parabola opens right or left. And the reason why we've never really studied y squared parabolas before in Algebra 2 or yet in Honors Pre-Calc is we're always focused on functions, and a sideways parabola would not pass a vertical line test. So we've never really talked about it because it's not a quadratic function.
Wouldn't y squared be the same as like square root of x?
Yep. Well, y squared would have both sides. Yep, so we'll look at that.
Oh, what if like x squared or x square root of x being the same as y squared but
Yep. Solve for y. What would you do? Add x. Square root both sides. And here's the part where, like a lot of times when we were always doing functions and we were doing inverses, we would ignore the plus or minus, but we know essentially in algebra, if you square root to solve, you should add a plus or minus to your answer, right? So now we're saying y is greater than plus or minus the square root of x. So now you have a positive square root of x, which is that square root parent graph, but you also have the reflection of that over the x-axis. Okay, so there's really two pieces there. Okay, let's graph that. What are some points on the parent function for square root graphs? Like I'm thinking x, y, what could I put into the square root of x? 4 gives me 2. 1 gives me 1. 0 gives me 0. Those are great points. So I'm going to plot that. 0, 0, 1, 1, 4, 2. And this graph is greater than, so it should be dashed. Now that's only the positive square root. There's also the negative square root, which would just be the reflection over the line y equals 0. So I have 1, negative 1, and 4, negative 2. This is y is greater than the square root of x, and this is y is greater than negative square root of x. Comes in two pieces. Are we okay with everything I've done so far? Okay. After you graph it, you should check to think about like where is it going to be shaded, right? So I'm thinking about shading, and I had suggested that we use a test point. So you don't want to pick any of the points that you put on the graph. So I don't want you 0, 0, 1, 1, 4, 2. When I pick points, I like to pick points that are on the axes, only because then one of my coordinates is 0, and I feel like that's an easy one to evaluate. So I'm going to test 0, 4. You can test anything you want. We should get the same result. Okay. You can choose. Do you want to plug 0, 4 into the original? Do you want to plug 0, 4 into the one where you solve for y? I'm going to put it into the original. Negative 0 plus 4 squared is greater than 0. 16 is greater than 0. True or false? True. So 0, 4 is shaded. And I'm not going to shade because it gets really messy on my smartboard, but that means that I must be shading all on the outside of the parabola. Okay? Now we got one other graph to do. This one I feel pretty confident with. It's a line, y equals mx plus b. So I'm just going to plot my y-intercept at -2. And I got a slope of 1, so I'm going to go up 1, right 1. And this one should be a solid line because it has the or equals to. So this is y is greater than or equal to x minus 2. And then you could use a test point. You could, hey, on this one you could use the same test point, 0, 4. It's not on either graph. Or I know that since it says y is greater than, I must shade above the line. So now I have my shaded area that is the overlap. I gotta stay above the blue line and outside the parabola.
And then you don't have to do line graded.
Yeah, I didn't have to test the line because it's y is greater than, and I would short test that. If I did test, it would come out to be, like if I tested 0, 4, it would be true for the line. And so I would shade up. Is that area bounded or unbounded? That would be unbounded because imagine it just keeps going, right? Just keeps shading over there. Okay, so this is an unbounded region. But even unbounded regions have something we call vertices. Vertices are the points or the corners where your curves intersect, right? They're like the corners to the shaded region. So this line is a boundary. But then when the line hits the parabola, I have a vertex to my shaded area. So I'm looking at this point, and then I got the curve, 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 and then I have a point right here where there's an intersection that represents a corner to my shaded region, and then it's just going to follow the line, right? No more intersections. Can you eyeball either on my graph or on your graph? What do you think those points of intersection are? What's that? Last one down one? Looks like positive 1, negative 1. And looks like maybe 4, 2. Now my drawing's not that good, right? It's not using graph paper. And so there are a couple different things I should do to make sure that I'm correct. One way I could see it is go back and really think about when I drew that line, right? I put my y-intercept at -2, and I went up 1 over 1, and it definitely crossed 1, negative 1, which I knew was in my table of values. Okay, so I know 1, negative 1 works. And then I could keep following my slope and make sure that it really lands on 4, 2 right there. It does. Okay? So if you have a good graph, you might be able to tell for certain, and you think about slope, that it actually is the point of intersection. Another thing you could do is take these points, 1, negative 1, 4, 2, and plug them into both equations or inequalities. What should happen is not that they necessarily satisfy the inequality, but they should make both sides equal. So if I were to check 4, 2, negative 4 plus 2 squared, 0 equals 0. 2 is greater than 4 minus 2, but 2 equals 2. So then 4, 2 is on both graphs. Check negative 1 and negative 1. Negative 1 plus 1 squared, 0 equals 0. This would be negative 1 equals 1 minus 2. Negative 1 equals negative 1. They check. So it should work in both inequalities, making both sides equal, even if it doesn't fit the inequality. The other method, and I just want to go over this in case you should get stuck, and like what if you plug them back in and they don't actually work out, right? How do you actually find the real point of intersection? Basically, you're solving a system of equations. So you have, what is it, negative x plus y squared equals 0, and y equals x plus 2, no minus 2. Okay. Now, I realize that they're really inequalities, right? But right now we're talking about the specific curves, and the curves are the equal points. So if you couldn't find, just by looking, what the points of intersection were, all you really have to do is solve the system. What would be a possible method to solve the system here? Elimination, substitution. Which one do you think looks easier? Substitution. How do you want to substitute? Plug in x minus 2 for y. Okay. Or what? So that would be y plus 2. And then plug that in. So negative y plus 2 plus y squared equals 0. And either way you do it, you're going to come up with something that is quadratic, right? This one will be negative x plus, and then I'd have to FOIL this out. X squared minus 4x plus 4 equals 0. So I'd get x squared minus 5x plus 4 equals 0. And that's x minus 1 and x minus 4. So I get my 1 and my 4. Now on this one, I'd have to go back and plug in for y. So maybe I'll do 1 minus 2 is negative 1. 4 minus 2 is 2. Checks out. Ruth is nice because all we have to do is distribute the negative, right? But she's going to end up solving for y first. And then you'll just have to plug in to get x. Okay? So if you ever get stumped or you're like not coming up with coordinates that work, then you can always solve the system algebraically. And that's going to come in handy tomorrow, because with the linear programming, you're going to have some graphs where the numbers are so large, we're going to scale the graphs, so you really won't be able to just count and look at the point of intersection. You'll have to solve a system. Okay? Any questions about what I did right there? Keep in mind for your homework tonight, when you're doing these graphs, that one of the main pieces that I want you to do is also label those vertices. Okay, so that's an important piece. I want you to take the time to do that. All right, last thing is a word problem. Okay, and this is very lengthy, so I would not recommend taking the time to copy this down. To me, that would be a waste of the time that we have together. So I pulled this problem from your textbook. It's in the 7.5 notes. It's on page 514. It's labeled as the checkpoint problem. So if you write in your notes right now that we're doing page 514 checkpoint, then when you see that in your notes, you know, okay, if I want to retry this problem or I want to take a second glance at this problem, I've just got to open up my textbook. Now, if you have your textbook with you, you could certainly open up to page 514 and read the checkpoint problem. It's the same problem, and read it in the book instead of on the screen. But what I want you to do here is, we're not going to necessarily go ahead and graph this one today, but I want you to think about, like, could you set up the system of inequalities? So it's a lot like what we did in the warm-up, setting up the system of equations, but this time you're going to have inequalities. So here's what you should do. Read through the problem. Double check what they're asking you to find. Use that to help you define your variables, and then try to write the inequalities. I'll give you a few minutes on your own, and then I'll tell you to start having conversations with your group and see if you guys agree. So remember, as you're reading through it, my suggestion to you is always pay very careful attention to what they're asking you to find. What they're asking you to answer or what they're asking you to find helps you define your variables. Okay. So define your variables. Once you have your variables defined, how can you use those variables to write the inequalities? You might want to throw out some ideas to your group members here and see what they think for what are your variables. Let's check in. Let me first ask this question. What are they asking me to find? How many bags of each brand? So that means your variable should be what? Should your variables be the nutrients or the bags? Or the brands? They should be the brands. So I would use X and Y. And X is the number of bags for brand X. And Y is the number of bags for brand Y. Okay. This one reminds me of, it was on your problem set, the speed of the airplanes. Okay. A lot of people just said in that problem, like, X is plane 1 and Y is plane 2. But then they gave you all this information about plane 1. They gave you a time, they gave you a speed, and they asked about distance. So what specifically about plane 1 was it asking? When you read the end of the question, it said find the airspeed of the plane. So then X was plane 1 speed, Y was plane 2 speed. And you use those things in your equations. So now we know X is the number of bags for brand X, Y is the number of bags for brand Y. How can we now set up some inequalities with X and Y? What's all the other information they tell us? They're telling us all about different nutrients. Nutrient A, nutrient B, nutrient C. Focus one nutrient at a time. We know brand X has 8 units of nutrient A in a bag. Brand Y has 2 units of nutrient A in the bag. It carries over onto the next line. And we have a required amount of nutrient A should be at least 16, right? So what kind of inequality could I write right there? I have X bags of nutrient or of brand X. How many nutrient A's do I have? 8X. Plus, how much nutrient A do I get from brand Y? 2Y. Depends on how many bags I buy, right? And I need those nutrients to add up to at least 16. So, greater than or equal to 16. Would one bag of brand X and one bag of brand Y be enough? No, because that would only get me 10 nutrients of A when I mix them together. Could I buy 2 bags of brand X and no bags of brand Y? Yeah, because then I'd have 16 nutrient A's in the mix. So now we're starting to see, like, okay, there's some points like 1, 1 isn't going to be shaded, but the point 2, 0 would work, would be in my bounded region. What are the other inequalities? x plus y. Where is the 3 coming from? 1 unit of nutrient B, 1 unit of nutrient B should be 5 units. So 1x plus 1y must be greater than or equal to 5. Next one. 7x plus 2y must be greater than or equal to 20. Yeah. Okay.
How do you know to add, like I get, like the written problem, how do you know to add, like, the stuff on brand A to brand, stuff on brand A to brand Y? Yeah, to be mixed, like, okay.
So they're going to take the 2 brands and they're going to mix them together, and in the mix you need at least that many. It's kind of like a strange question, I know, but yeah. So that's just saying to fit these what I would call constraints or inequalities. Like you have to have at least 16A. Can you have more than 16 nutrient A? Sure. Right. If I buy 100 bags, will I have enough of each? Oh yeah, I'm gonna have way more than enough, but I probably don't need 100 bags of dry mixed food. So we're kind of gonna look at tomorrow what's the optimal number of bags I should buy to meet all the requirements and to like save the most amount of money. That's what linear programming does. Now there are 2 other requirements that I think should be there because we're working in the real world. So imagine me going into PetSmart. What is the least amount of bags of brand X I could buy? I have to buy 1? 0. Am I allowed to go into a store and not buy anything?
No.
Yes, I am. So the least amount of brand X that I should buy is 0, and the least amount of brand Y is also 0. The problems that we see tomorrow aren't going to say anything about this specifically, but trying to get your brain thinking about this. If you're living in the real world, you're not going to walk into PetSmart and ask for -1 brand X, right? You could say, I don't want any brand X. That would be fine, but you're not going to say less than that, okay? So we're going to have all of our real world problems are going to be restricted by at least 0. Sometimes it could be more, depending on the word problem. Okay. Any questions there? That one's kind of a funny one, so that's why I wanted to like have us look at that together. It gets really confusing because there's X and Y and there's A, B, and C. So really important, remember how last week I said I'm going to push you to define your variables. And you'll define your variables based on what the problem says to find. Okay, so you have a homework assignment. I'll come around and give you a piece of graph paper if you want it. If you choose not to use the graph paper, that's fine. You can just turn it in to me before you leave today. There's, 5 problems that are required, 7 if you do them all. So kind of split up your page into 4 so you'll have enough space for everything. And then there's also some reminders here. I'm not going to be here on Friday morning. Thursday afternoon is going to be a little bit crazy. I might not be around. Start communicating with me via email. Don't wait until the last minute. You're probably not going to be happy with my answer if you do. The Chapter 3 test retake deadline is tomorrow, and I currently don't have anybody who has completed the work for that. So if you were planning on doing a Chapter 3 test retake, you should be seeing me ASAP. Remember, on these homework problems, you should be graphing, but also labeling the vertices so that you can check tomorrow, do you have the right points of intersection? That's important for linear programming.